welcome back to the next little update of the scripting language. Math64, we're calling us, I guess, PlayBASIC, whatever the hell you want to call it, I don't care. Since the last time, we've externalized the scripts, so they're just loaded from a text file. See if this version here compiles. I didn't bother to check before. Let's check why we've got a syntax error in the code. And we do because this expression here is invalid. So we don't have an error for that occasion at the moment. We've got a function here that normally takes one parameter that's being passed two parameters. So it should give you an error like, incorrect parameters for this particular function. I don't know how it's going to work at the moment. We'll go into how errors are actually, I've changed the way errors work, and we've got some errors there built into it. That's what we're testing. So flip back here to, this is where the source code is, scripts, and that was the if examples, I think it was. So we've got a new thing, we've got a comment. We only got one type of comment, that's just the double divide, double slash, whatever you want to call it. Just hit save. I haven't actually set this up to just let you modify the script and recompile. Just too lazy, I guess. So we've got no error status here. Our console is looking pretty good. So it's all compiled and okay. We're halted behind a break. So execution of that script is about 490 million instructions per second, but it's very biased because that script has a bunch of branches in it. So we have whole pathways of code that are not being executed. So don't get too excited by that. For the differences between this version and the other version, we've got some error messages built into the library. We've got externalized the code from it as well. We've got some slightly more robust things. I can't think what was added now. I updated it actually a week ago, probably maybe 2 weeks ago now, and meant to do this back then, but had some troubles with real life stuff getting in the road, as they do. I've kind of forgotten some of the things I was working on. If we just jump back to the forum, I know it was in a post there. Just refresh my own memory for a second. Oh, of course, the copy to and copy from thing. So I've been mulling over ways of how to communicate the script variables with your own variables. I thought, well, I can make a fancy solution, I can make a simple solution. So I thought we'll go with a simple solution, and if it's even worth doing for performance reasons to write scripts that are exported to Math64, then we'll worry about a more eloquent way of doing this. At the moment, what we're actually creating pretty much is really a fast just trying to think what it was called. There's a built-in function, a built-in way of solving floating point expressions that has the same concept actually, where we have, I think it's under math. It's called FastCalc anyway. It's pretty well unknown. There we go, math expression processing FastCalc. The internal version doesn't have expression solving at all variables. You have to lay the expression out in the order in which it's meant to be executed. So if you want multiply is done first, you put your multiply instructions first, and then you put your additions and etc. after that, because it doesn't worry about precedence. Now the beauty of this is these FastCalc expressions, you could if you had more than normally about three or four stacked operations like mults or divides or additions or subtractions, then you get a benefit. And depending on how much of your expression you can stack up and restructure it in a way that was comfortable, you could get quite a big benefit. But some of that benefit was lost in old versions of PB because there's like a conversion from how the variables are stored in one place into this new solving. So it's copying data from there and putting it in there all the time. Now we have the same kind of problem with our externalized scripting engine here with Math64. If you wanted to do very simple scripts that just took a few values and added them together, then calling the script and initializing the script and to have it do something very simple is way more expensive than just doing the additions inside PB, which is the point I'm trying to get to here. But if we have a bunch of a decent block of code, and provided we can rearrange our logic to suit the way the scripting engine works, then it probably is way faster to do this kind of stuff in a script and then just copy the results back. What we do have is, to do that, we've got these functions in the library here. We're looking at the raw library itself. This is just the test I'm putting together. I'll clean it up a little bit, and just drop it on the forum as a library. You can use it as is. This is about all the documentation you're ever likely to get about it. So I'm assuming that you know PB up front. If you don't, then don't come asking me dumb questions because I won't be answering them. Like, what's an if statement? Hey, read the manual. Anyway, so we add these functions up here to do where we can ask the compiled script where a variable name is within it. We can get that variable name as a particular data type, so we can read it as a 32-bit float. There should be ones there really as well. We probably need one there to read as an integer as well, to just help with less conversion. So if we can just ask the script, hey, give me an int of this, give me a float of that, then we don't have to do more work to it. Like if we just have a float and we want it as an integer, we've got to recast that on our side. That's another fall through the runtime to solve these things. I'm thinking of performance here, Anyway, so we've got these new functions here. The internal functions are called copy to variables 32-bit float, and there's a copy from. So the principle really is that you have, I'll just mock up some code up here, let's say. Actually, I think I talked about it on the forum. Yeah, I did. So the section of code here, I hope you can see that on screen, but that's the PB structure. Now they're all floats, they're all 32-bit floats, because what we're going to do, ideally, is when we create something of this structure, we're going to get a pointer to that thing and then use copy to copy all of those fields there into their 64-bit cousins inside the script. The script would do whatever it needs to do, and then once we're done, we have one copy to copy it out. So ideally, that's going to save you a bunch of function calls, copying separate variables, but you do need to keep these in order. So the status variable has to be the first one in the variables declared here. Your x and y have to be declared the same order, your speed, whatever this structure is representing, and they do have to all be floats. That's the price we have to pay in this regard. because the Math64 is purely floating point. It doesn't have any clue of integer, so we can't do casting when we copy it across without giving it an elaborate way of casting values. We probably could, again, if it came down to a situation where it was very efficient to do this and quite practical to do this for bigger programs, then yeah, sure. More than happy to drop in some code, a solution to do something like that, like have a bit mask, and you can tell it to copy, 32 fields, but have a bit toggle for if it's int or float. Just keep it nice and simple. Is it integer or float? Copy it. That way we have minimal decisions inside the copy loops. So it's going to be very close to actual just memory copy speed in general. I think at the moment, with the problem with this kind of setup here is it's probably too low level for people to wrap their heads around. What we might do is wrap up this process behind a bit of a typed array, an index and something like that. So you would compile a bit of code, it would give you a program index of the compiled program, and you would query against that. Like, rather than have to look at the structure of the program here, you might just have a query function, I don't know, get program, and then rather than even have a bunch of get programs and then or get program functions that do specific things like get the name of the program, get the size of the program, get the last error of the program had, or the current line, or get a variable from the program or something like that. We might just have something in text, we might have a result here saying, hey, what if we wanted to know, well, you probably need tags in here as well. You need some way of, because on the library side, you have to understand what these parameters are actually doing. So you could get like get program. Well, sorry, you need the program index in here, like that'd be your index, and then you have like a command as a string. We'll use the one, the thing below here, and we'll say error status. Now, you might think that's kind of convoluted and a terrible idea, but the beauty about this is that you wouldn't need to then have all of this other stuff declared inside the library, visible on your side of the conversation. It can be hidden away inside the library, and here, when we call get program, it works out what this particular instruction is requesting, and it works out what program this thing is, and maybe we could have a recompile or something like that. Well, that might be the error status, and like error message or something like that. Again, we're thinking on the fly. Internally, modern 165 works like this. If you're wondering how you could do more complicated things with scripts, I'll leave this to your imagination. But one thing that you could do, you might think, well, how can I make an array in the script side? And when it doesn't support arrays, because this is script and you're manipulating this thing yourself, pretty much. What you could do is treat this whole thing, you load the script in as a string, have particular keywords here. Maybe you want to you need a special character to do replacements of. I'd probably use like index or something, you know. So you might have a couple of these different keywords. Yeah. And what it would do is it would replace this variable with a counter index. So it would then, your code would just use a simple replace operation. It would load this all into a string, and then I can treat A as if it's an array by just by declaring A like this, even though it's not an array. I could go var A1, A2, A3, sorry, put our A0 in there as well. So this is the equivalent of doing, in PB land, going dim A3. It's not beautiful, you know, we don't have an index per se, but we now have 4 chunks of memory that are consecutive. So what you could do is you could use this index down the bottom here, and let's say you had a for next loop that you wanted to iterate across these 4 values. Yeah, you have some sort of tag here, you know, I don't know, for next or something. For next, and you might have a block there, another block at the end to say this is the end of for next, or whatever I could call that thing before. So I skim through, would find this, go, and in this case here, you would just do a raw replacement and then dump the text out. So anytime this A here is visible, it's going to replace it with, on the first pass it's going to be A0, second pass is going to be A1, A2, A3. So they've got 4 different variables stored in the script memory, plus all of this code here is copied out 4 times and modified to suit. Sorry, it's a very convoluted way of trying to get that example out there, get that idea out there. But you could cobble up a way of doing, having the script do more work by actually generating code on demand. What I think is probably a good idea actually is if you did, these are just cut and paste of what was built into it already, but if you had a bunch of coordinates, for example, possibly vectors, I guess, you could unroll the whole thing to do the whole vector individually, even though there's no loops. So you won't be penalised that much for it either, because I guess you would if the script became massive. But if it was simple enough, you could make it work. I was thinking about see, one other thing actually is that there is a part of PB called the vector stack, and it was implemented as an experiment. A few things that aren't documented that are still in PB are experiments, and it's one of the ones that's actually it's not supported by 165. You need older versions of PB for this to work, but you could define a block of vectors. You know, you sort of had type here. I think they were just, you know, vector 2 or something like that. Whatever it was. It's been a while. There's a few examples on the forums, but there's very little information about this stuff. It never made its way into a full version of PB. It was never finished off because no one cared about it. But what you could do is so here's my vector with just an X and Y coordinate. think it actually works in three-dimensional vectors. So we have x, y, z, and then we have our group of vectors that we need. This might be, I don't know, we'll call it particles because that's just the way things are at the moment. It's a name that comes to mind. So we might have our position as vector 3. Whoops. Something simple. So this is our speed or velocity. Here we've got like a gravity or some sort of external force, like, you know, whether it's gravity or wind or something like that in the particles. Or, I don't know. I'll call it gravity. What vector stacks let you do is you can define a list of these simple instructions. It has no scripting front end. This is why it was kind of abandoned, really. It has no scripting front end, but it lets you do additions, subtractions, multiplications of these vectors by using their index by using this structure here as like a stack. So this would be vector 0, this would be vector 1, 2, and then it's got this. Then it had these kind of simple functions where you could go, you know, add. You want to add. I think it was you needed 3 of these things actually. You want to add. I think it was destination and then source. So you can add speed onto position, and you could do like an addition of your gravity vector to here. And because the solver for this is actually working in vectors behind the scene, this is a much quicker way of doing vector operations than in PB. And even in Math64, which brings me to the point really of that terrible sort of sidetrack conversation, is that it's something we probably could drop into Math64 and not really change things up that much. I'm not quite sure how it would fit, but I do think it would fit. You know, to use this example here, if we just declare something as variable, we go, okay, that's a 64-bit variable. But what if we have internal concept of just, you know, just call these vector 3. We can have, you know, we couldn't have a because it's already defined as a variable, so we couldn't have that. But we could use our, what did I say before, position, speed, and gravity. So position would equal position plus speed. Speed equals speed plus gravity. And that would do additions of the 2 vectors here, position with speed. So the x fields, the y fields, and the z fields are being all added to at once. And because that would be a single instruction in the runtime, you gain a lot of performance benefit there too. And we could catch this situation here where it would rewrite the destination for us by using the same tricks we use with just catching normal expressions. If you wanted to use the fields for something, you would do the same thing. There's no print in this actually, so we could go a equals position.x. So now we're copying the x field from this. It would be 64-bit vectors too, by the way. I guess you could probably have 32-bit, and this is even getting more crazier now. You could probably, because we wouldn't have a lot of these instructions, we'd only have a few of them. It might not alter the characteristics of the runtime that much, so therefore you could probably have a 32-bit version and a 64-bit version. Don't quote me on that, I haven't tried it, but I think it would fit into this and it would feel more natural to people than the vector stack stuff and, you know, the FastCalc stuff that's already built into it, if it actually performs better. If it doesn't, it's just a novelty you can tack on the side of your program and do, you know, have externalized scripting. You know, change behaviors of your objects while the game is running, which is a pretty cool thing for if you're comfortable having, say, the art guys or designer guys help with doing scripting and, you know, some math here and there. It's going to be ugly, but, you know, I'm not trying to reinvent anything here. We're just trying to create a solution for missing out on 64-bit that's going to, we don't have to redesign everything else to suit it. I think eventually we'll just go, we'll implement this stuff into PB, but even my gut feeling is actually, even if we did that, it would still be beneficial to have this kind of solving engine outside of that. Because PB is a big blob of this solving code, the runtime, sorry, the VM in particular, which is the runtime. And the more of these things you add to that blob, you can have unwanted consequences, like it actually makes something slower. So you've got to be careful you don't get too excited and try and jam everything into it. But you still need to be conscious about how your instruction set lays out. And this is what I've learned over the past probably 15, 20 years doing this thing, is sometimes we underestimate how well things work, and other times we overestimate how well they work as well. I like this idea a bit, and I think it's worth actually having a bit of a look at that. I think it will fit in relatively easily. But don't come crying to me if it doesn't make its way in. Time is not what it used to be, mate. Anyway, enough of this waffle on this thing. I won't save that. Get back to what we're doing before, and I'll put this video together and upload another snapshot of where we are with it and have a play with it. And if you have some weird and wonderful ideas, you know, don't worry about it. Don't hold them back, because you might have just the perfect idea at the perfect time. Anyway, thanks for listening, and I'll see you next time.